Thank you. So this work is joined with Yair Sovereign, Russell Power from NYU, and Marcos Aguilera from MSRSVC. So our student Yair did most of the work for this project, but he cannot be here to give the talk because he has just very recently become a father. Okay, so consider your typical web startup today. Say I had this great idea of running an online social network for pets. Let's call it Petbook. And what am I going to do? I'm going to build this website using the popular LAMP stack. And then I'm going to rent servers from some data center provider to run my application front end and my favorite database backend. So things all go very well until one day my web service goes down because the entire data center has failed. Of course, data center failure is rare, but it does happen, and I'm sure everybody here has heard about the recent Amazon outage in their East Coast data centers that has brought a lot of websites down. And since my cat book application is very popular, I don't want any extended downtimes. So I'm going to geo-replicate. And I'm going to run servers from 2 geographically separate sites. And since I'm already paying for the physical resource, I'm also going to serve user requests from both of these sites. It's easy to replicate application logic. I'm simply going to run multiple Apache instances on each of my sites. But, all of a sudden, I cannot run my MySQL databases because, it will not allow me to read and write from multiple sites. So I would need a geo-replicated storage system that can deal with the access of, accessing replicated data from multiple sites. And I also like to have transactional support, which I originally had with my MySQL database. And web applications really treasure their low latency operations. So what do they do today? They are basically going to go with eventually consistent storage. And that is a big pain, actually, for both users and application developers, because users and app developers are going to see many anomalies that are possible with eventual consistency. For example, in Facebook, I might see a particular message on my friend's wall. Later, when I reload the page, I can see that message disappear. And then when I reload the page again, I can see that message reappear, which is very annoying. Or, I get a notification that says my friend commented on my photo, but then when I go on my wall or in my photo album, I don't see that particular comment. So eventual consistency is not good. What other choices do we have? So here, let me plot the existing semantics that we have for transactions along a spectrum from strong to weak. So at the rightmost extreme, we have eventual consistency, which is the weakest, have all sorts of anomalies, but it's great for performance because it allows transactions to be replicated in the background asynchronously. And on the left extreme, we have serializability and snapshot isolation. And these are popular semantics with single server database systems. They are great for semantics. They have few anomalies, and snapshot serializability has none. But in both of these semantics, it requires a transaction to acquire logs with remote sites before it can commit. So it's not good for latency. So you might ask, can we find something in the middle? Are there any existing weak semantics that can allow us better performance? But in fact, we have found no weak semantics for transactions in the database literature that will make sense in a multi-site setting. So we take it upon ourselves to find a new semantics that can have good multi-site performance and support asynchronous replication and have few anomalies. So it will then still be useful to application programmers. In the rest of this talk, I'm going to first discuss this new semantics we propose called parallel snapshot isolation, or PSI for short. And then I'm going to describe a system design for a key value store called Walter that can realize this semantics very efficiently in a geo-replicated setting. And lastly, I'm going to tell you about 2 applications that we have built to run on top of water, and show you that PSI actually helps gives very useful guarantees to these applications. Okay, let's start with semantics. So from the name, as the name suggests, you will know that PSI is going to be a relaxation of the classical snapshot isolation. So let me just briefly summarize the property of snapshot isolation here before I describe our semantics. So conceptually, in snapshot isolation, there exists a global timeline in the system. And all of the transactions are going to have a commit time ordered along this global timeline. And after the commit time, the updates of the transaction is going to be visible. Okay? And snapshot isolation provides 3 guarantees. The first guarantee is snapshot read, and by which I mean a transaction is going to read a snapshot as determined by the beginning of that transaction along this global timeline. And the second property is snapshot isolation does not allow write-write conflict. That means if there are 2 concurrent transactions that happen to write to the same object, one of them must abort. So in this picture here, my pink transaction, my blue transactions do not write to the same object, so both of them can commit even though they are concurrent. And the last property is snapshot isolation preserves causality, and this is a byproduct from simply having a single global timeline. So this is a derivative from the global timeline. So having a single global timeline is what makes it inefficient to implement snapshot isolation in a multi-site setting, because in order to achieve a global ordering of all of the transactions in the system, when at the time I'm committing a transaction, I have to talk to the remote site to find out this ordering. Okay, so in order to get better performance, naturally, we are going to relax this single timeline constraint. And so in PSI, we're going to allow multiple timelines, 1 per site. Okay, here we have 2 sites, so we're going to have 2 timelines. Okay, and each of the transaction is going to have a commit time along its own timeline at the site that is executing. And then asynchronously in the background, it can get propagated to other sites and sort of becomes visible there along those sites' timeline. And PSI, apart from this relaxation that now we have multiple timeline, it provides very, very similar guarantees as snapshot isolation. So here are our 3 original properties for snapshot isolation, and we have very minimal modifications here. So for parallel snapshot isolation, instead of reading from the snapshot according to the global timeline, each transaction is going to read a snapshot from a per site timeline. This per site timeline is going to include all the transactions that have been committed in that site, as well as a prefix of transactions that have been committed in other sites. And it's also, like snapshot isolation, it's going to prohibit write-write conflict and preserve causality. So some of you are curious, might be wondering how the hell are we going to prohibit write-write conflict without doing some sort of coordination among remote sites. And please hold off that thought for now, and I will address this concern later when I talk about the system design. But for now, this is the gist of parallel snapshot isolation. And you might wonder, what does this mean concretely to application programmers and end users? And in particular, what kind of anomalies, new anomalies that I'm going to get by adopting this semantics as opposed to something like serializability. So here, I'm giving you a table of all the anomalies that are possible under different models. And I'm comparing PSI with snapshot isolation, serializability, and eventual consistency. And of course, eventual consistency is going to be bad on all fronts. So the first 3 anomalies are your classical database anomalies that you can just get by opening up a database textbook, like dirty read, non-repeatable reads, and lost updates. Parallel snapshot does not have any of them. And the next 3 anomalies are related to state forking, meaning that when 2 concurrent transactions execute, they temporarily don't see each other's update. And because PSI prohibits write-write conflict, so all these fork states can always be merged in the end. So there is never any conflicting fork, which is possible under eventual consistency. But PSI does admit the two other types of fork, the short fork and the long fork. And let me tell you in more details what I mean by these two types of anomalies. Okay, so the first one is short fork, and I'll give you an example of what short fork is. So in this example, the state of the system progresses happily along until two concurrent transactions starts executing, T1 and T2. And while they execute, they don't see each other's update. That's why the state, as observed by these two transactions, have forked. And at commit time, the state is going to be merged back together because there is no write-write conflict allowed in snapshot isolation. So the state is merged again, and everything is happy. And this anomaly is also allowed by snapshot isolation. And in the database literature, it's called write skew. The other type of anomaly that PSI allows but is not present in snapshot isolation is what we call a long fork. Again, the global state progresses happily along until we have two concurrent transactions executing at different sites. So they don't see each other's update as they execute, so the state forks. But this time, when both these transactions commit, they still don't see each other's update. The state remains forked. And it's only until the updates gets propagated to both sides that the global state is merged again. And again, since PSI does not allow write-write conflict, the state is guaranteed to be able to merge. And this is what we call long fork, and it's not allowed in snapshot isolation, but is allowed under PSI. So we have looked at a bunch of web applications, and this long fork is does not affect correctness in any of the applications that we have looked at. And this long fork gives us the performance that we need to have, to make PSI work well in a multi-site setting. In the same sense that admitting the short fork allows snapshot isolation to have better performance and serializability in a single server setting. Okay, that's about all the formalism. Now let's look at how the actual system design of Walter, a transactional key value store that implements PSI efficiently. So here is the overall architecture of the system. For example, if I have two sites here, each site is going to have a Walter server that handles the storage as well as the coordination necessary for committing a transaction. So the Walter client can talk to the server to start transaction, read, write, and commit. And the Walter server across different sites are going to talk among themselves to replicate data and to coordinate to ensure that PSI is enforced. Okay, of all the design choices that we made for Walter, the most challenging part that we have to address is to avoid write-write conflict efficiently across sites. And Walter uses two techniques to do so, and that is what I will tell you about next. So the first technique, preferred site, is based on the observation that in almost all of the web applications, we can structure the application such that most of the writes can be directed to a single site. In my cat book example, each user I can direct each user to log into a single site where he or she is going to modify her data. So, I'm going to associate each user's data with a preferred site. For example, I'm going to associate Bobcat's data with site 2 and Alice Cat's data with site 1. So when Bobcat logs into system, he gets redirected to site 2, and where he will be adding photos to his album and editing the photos and so forth. And writes at an object's preferred sites are fast, because in Walter, they don't need to do any cross-site coordination in order to commit that transaction. They simply commit locally and gets propagated asynchronously to the background to the other sites. And if, God forbid, Alice Cat wants to modify Bob's photo, which I don't know why, this is going to be the rare case. We have to resort to doing a cross-site two-phase commit. And hopefully you can structure your application such that these two-phase commits are very, very rare events. Well, the preferred site solves a lot of problems, but not all. In particular, in our catbook applications, we found that many objects are modified by many users. So they are modified from many sites. And in this example, Bobcat wants to, Bobcat answers the befriend request of Eve. So he's going to perform an operation to write, his name to Eve's friend list. And similarly, Alice Cat may also befriend Eve and also perform modification on Eve's friend list. But Eve's friend list can only have a single preferred site. So no matter where we put the preferred site, half of our users is going to incur on cross-site two-phase commit, and that is no good. So we solve this problem by introducing counting set, which is a data type that does not do read and write, but rather supports commutative operations. And therefore, this data type by design is free of any write-write conflict. So let me show you how we are going to implement this friend list object using counting set. So in this example, again, Bobcat is going to befriend Eve. So instead of writing to Eve's friend list, he is going to add his name to Eve's friend list counting set. And this is going to generate an entry that says, set element Bob has a count value of 1, and then asynchronously propagate that operation in the background to the other site. Oops. Okay. Why is that? Okay. So if concurrently Eve is also befriending, if concurrently Alice is also befriending Eve, then Alice is also going to generate this operation that add her name to Eve's friend list counting set and asynchronously propagate that operation in the background to site 2. And what is neat about the counting set, is because the add operations all commute, and the set is unordered, and eventually when the add operations gets propagated to the remote site, they are going to add the corresponding entries, and the state of the counting set converges to the same thing. And we add the counter values, so it's not just simply a set. We add the counter values because we want to make all the add operations and all the delete operations commute with each other. And the caveat for this, of course, is counting set is not exactly a set. So application developers have to deal with counts. For example, what it means for application if it reads a count value of 2 or a count value of -1. Okay, so far I've talked about the normal operation of Walter. When in the face of a single site failure, Walter provides 2 options to deal with it. The first one is a conservative operation, where Walter allows me to choose consistency over availability, and simply going to block all the writes whose preferred site has failed. The second option, we're going to choose availability over consistency and going to reassign the preferred site for those objects whose original preferred site has failed. But by doing so, we do run some risk, and the risk is certain committed operations that have not yet been propagated to any of the remote sites might potentially be lost if we also start writing conflicting operations. But this is no worse than any of the existing asynchronous database replications. So now it's time to talk about applications. We built 2 applications on top of Walter. The first one is Wall Social. Now I just rename it as Catbook. And so in these applications, the wall and friend list objects are both counting set. And an example transaction in this setting is the befriend transaction, where Alice and Bob befriend each other. So this transaction is going to read Alice and Bob's profile object, add themselves to each other's friend list counting set, and is going to add a wall posting on both Alice and Bob's wall to brag about this new friendship. And by having a transaction, we can make sure we never see the anomaly such that you see that Alice befriend Bob, but then when you click either Alice or Bob's friend list, you don't see the new friendship. And the second application is the third-party Twitter clone that's originally developed to run on the Redis key value store backend. And we switch this Twitter application to using the Walter backend. So in this application, the timeline of each user's tweets is a counting set. And whenever a user posts a tweet, the transaction is simply going to write a status object, and then for each of the follower of that user, is going to add that new object identifier to the follower's timeline counting set. Okay, now let's see some numbers. We have implemented Walter in C++ with PHP bindings, so it's easy to develop web applications on top of Walter. And our experiments run on Amazon EC2 up to 4 sites in different availability regions. And so here, the first graph, I'm going to show you how Walter scales. On the x-axis, I'm going to show you different sites that runs this experiment. And on the y-axis is the aggregate transaction throughput across all of the sites, where each transaction is either reading or writing a random 100-byte object. And we can see Walter scales pretty well, especially for read operations, because reads are completely independent. And for the write operations, it also scales, but not really linearly, because we are doing full replication. So at the 4-site experiment, for each operation, there's simply more work to be done than the other setups. But it's still, the performance increases with the number of sites. So here, I'm showing you the application latency in the Walter social application. And this is a CDF graph. On the x-axis, we have the operation latency in milliseconds. We have 3 different types of operations. And we can see that the latency of these operations are great. The 99 percentile are actually less than 15 milliseconds. And these transactions are much more complicated. In particular, the posting on wall transaction is going to read 2 objects, write 2 objects, and also update 2 counting sets. So for the Twitter application, let's look at its throughput here. Again, for different types of operations that's commonly accessed in Twitter, like read users' timeline, posting a tweets, and following each other. And we compare the performance of retweets running on Walter with the original Redis storage backend. So Redis only runs within a single site. And we can see when we look at the performance difference between the blue bar, which corresponds to Redis, and the black bar, which corresponds to Walter running on one site, we can see the performance similar. Walter is worse, but that's the price we pay for having transactions. But Walter can allow us to run this application across multiple geographically separate sites. And with 2 sites, we almost can double the performance. There is a vast amount of related work in the area. And in the cloud storage systems, there are no existing cloud storage systems that provide both transactions and allow for asynchronous replication. And in the database literature, as I said before, there are no weak semantic models that make sense in a wide area in a multi-site setting. And the folks there are concentrated on providing serializability or snapshot isolation across sites. And this is not going to work well for our low latency web applications. And lastly, there's counting-free replicated data type, of which counting set is an example. And except Walter uses counting set in a transactional setting. So in conclusion, I've showed you a new weak semantics called PSI that is particularly good for geo-replicated storage. And it allows fast commit and prohibit write-write conflict and preserves causality. And I've also shown you a key value store that realizes PSI efficiently. Okay, questions?
Hello. Hi, Mark Shapiro from INRIA. This is actually not a question, it's a couple of comments. So first of all, this is really nice stuff, and geo-replication and asynchronous replication is the way to go, and using conflict-free replicated data types is the way to go. So the 2 comments is, one, that we actually have a proof that the PSI protocol is just about the best you can do in a geo-replicated setting. You cannot have full SI. It doesn't work. The second comment
That
is...
is awesome. Thank you.
And the second comment is it's really too bad that you chose C-sets as your CRDTs because they have anomalies. We have much better sets for you that have much better semantics. And we also have sequences which would have been better for your timeline.
That is awesome news too. Thank you.
Yeah.
And yeah, I want to make a comment. So C-set is just one type of, one kind of data type that does not have any write-write conflict. And we can support other data types, that have similar properties and maybe easier for application programmers to use. So yes, feel free to design your own.
Hi, Doug Terry, Microsoft Research. So with counting sets, you avoid write conflicts, and you would avoid write conflicts even if you had eventual consistency. So it seems to me that the main thing you get out of your snapshot isolation are things like repeatable reads. But I didn't see in either of your examples of where they benefit from those properties. So can you explain to me why the type of applications you talked about need snapshot isolation and would not be okay with weak consistency reads?
Hold on. So eventual consistency have problems other than the issue of being able to resolve conflict. So you can read something. For example, you can read some element in the set, and later it disappeared, even though nobody has deleted that element. And with counting set and with PSI, this will never happen.
Right. So my question is in your applications, is that important?
Yes, because my original example of you see Facebook, you see some message on my friend's wall, and later on the message disappears, and later on you refresh again, the message appears. I mean, I personally find that kind of weird. So, well, if people are okay with that, then they're okay with eventual consistency.
Hello, Mesam Yobande, Yahoo Research. I guess the obvious question is that how reasonable is this assumption that developer can come up with changes of the write operation to these counting set operations. But I'm going to assume that this is feasible and developers could easily come up with that. My question is that what is specific about the wide area network to apply this idea? Why can't you apply the same idea to a single data center?
Okay, excellent question. So I think the short answer is within a single data center, I believe, and other people have demonstrated, it's possible to achieve snapshot isolation. And if that is the case, why go for a weaker model? So I think that's the short answer. But
in a single data center, it doesn't sound weaker, does it? Because if you have counting set, then you transfer the write-write conflicts to actually not write-write conflicts, because it doesn't matter if you have conflicts or not. So it doesn't sound weaker. We just put more effort on developer to come up with the right operation.
But the application programmer does have to deal with the kind of slightly strange semantics of the counting set.
Yeah, so it's not weaker, it's harder.
Yeah, so if you can provide a perfect set, with snapshot isolation, within a single data center at reasonably low cost, then you might want to do that. So it's really like a trade-off you make with the wide area that with slightly stranger sets, in exchange for good performance.
Thanks.
Okay. Thank the speaker again.